Welcome, everyone. My name is Helen, and this is the BlindAI webinar hosted by the Confidential Computing Consortium. We are a community focused on open source license projects, securing data in use, and accelerating the adoption of confidential computing through open collaboration. Everyone is welcome. We are a transparent and collaborative community. And feel free to ask questions in the chat at any time during the presentation, and we will get to them. This webinar will be available on demand on YouTube later. All right, let's have our speaker for today introduce himself. Corentin, go ahead.
Thanks, Hélène. So I am Corentin Lauvergeat. I am the head of security engineering at Mithril Security. I'm working on confidential computing. It's been like three years now. And at Mithril Security, we are building secure machine learning products that are leveraging confidential computing. So today I'm going to talk about BlindAI, which is our open source secure remote machine learning inference solution. And this solution is using Intel SGX in order to protect user data. So before we dive in, I'd like to kind of talk about what we're trying to do when we're talking about machine learning inference and security, and what kind of challenges we have when dealing with the security guarantees we want to offer, and what confidential computing can bring to the table to answer this issue. So, security and ML inference. The goals in machine learning inference is to have some security while keeping performance and having something that is easy to use. It's important because the performance in machine learning is critical. Most applications of machine learning are already using things that relies on a lot of compute power. So if there is too much overhead, it won't be practical to use security solutions, and so it might not get adopted unless it's for very specific use cases. Another thing to consider is how easy to use and easy to adopt it is. Because if there is too much complexity in switching, because most people are not already using secure solutions. So if it's too much trouble to adopt these solutions, then people will just say that they cannot do that and they won't secure the data at all. So we'll see that with existing solutions, this is usually the main issue. When we're talking about security, also there are different objectives, different property we want to have in machine learning inference. We want to have to protect the user data, the input that is fed into the neural network. We don't want it to leak. Second, we want the computation integrity properties, that the model that is basically we want to make sure that the output that we get is really the output of the model, of the right model, and that this output has not been tampered with by an attacker or someone malicious in between. And finally, it's not always the case, but usually we want to protect the model intellectual property, because machine learning models are getting more and more costly to train, more and more costly to develop, because there is also manpower in order to develop new architecture, to curate the data sets. And for a lot of companies, this is very variable. So they want a solution that also safeguard their intellectual property. So faced with this kind of properties that we and objectives want to have in terms of security for for machine learning inference, we've got already other solutions than confidential computing. Existing solution can be on-device machine learning, homomorphic encryption, for instance. So let's dive into, let's see basically what trade-off we've got with them. So for on-device machine learning, it's done. It's basically machine learning that is done on the client side, where the client is running the model. So because of that, if we take back to our 5 points, in terms of performance, it really depends on the user device capabilities. But while some devices are powerful, you usually have to consider the majority or even your the devices that are that have the lower capabilities in order to be compatible with them. So usually you won't have that much performance, or at least not the performance you could have on a server. So this puts a restriction on the kind of model you can run and the size of them, and usually the accuracy of the model suffer from that. Another thing is that it also has to be, we were talking about how easy it is to use these security solutions. And usually on-device machine learning is a bit hard to use. There are tools to help, so it's getting easier, but the main problem remains that you need to target multiple platforms. And it's hard to optimize for all of them because they have different constraints, different capabilities. So it adds to complexity and predictability. In the end, you are also faced with the limitations of user devices, the RAM, the disk storage. You cannot, for instance, put a big model like Stable Diffusion, which will take a lot of play. It won't even be able to store it on your user devices. So it's a big problem for people that want to deploy these powerful models. And finally, of course, if we are talking about portable devices and you are running like this kind of inference on a regular basis, you need to be careful about battery life, because compute heavy usually drains the battery. Compute heavy, power heavy, sorry, computation can drain the battery. So those are basically on the performance and the easy to use sides. On the security side, you get you get to protect the privacy of user data, because the user data never leaves the device. Actually, it's hard to be to do better than that. As long as the user trusts the code that is running on this device, then it's okay. You also get model execution integrity. But and that's usually a big con of a big problem with that is you can't protect the model intellectual property because you've shipped the model to the user, and even if there are ways like to obfuscate the model, in the end there are ways to extract the model. So you will be faced with these challenges. So for a lot of companies, this is not a possibility. Now let's move on to homomorphic encryption. Homomorphic encryption is usually used on the server side, so we don't have like the limitation about having to take into account each device's specificity. So that's good. The trust is also very strong because it's based on cryptography. So that's good. But unfortunately, the big issue is that the performance is bad. You've got usually 1,000 times performance overhead. So you cannot really, for big models, it's almost impossible. And also it's hard to adopt. You cannot just put your model and accept it to use homomorphic encryption to secure it. You will have to basically change your model in order for it to satisfy some cryptographic constraints. For instance, you will want to have quantization and making sure that really for instance, it deals with things in finite fields because the underlying cryptography is dealing with usually with those. There are different ways, but you cannot usually use floating point numbers. So you have to deal with some compilers that will adapt your your model, and you will need to if you really want to benefit from all the benefits of homomorphic encryption, you will even have to maybe think ahead when you're designing your model in order to satisfy those constraints. Not really something that you can swap easily. What we get in terms of security, we get the privacy of user data, but we don't get the execution integrity, which we wanted. There are ways to get it, to add it on top of it, but then it adds on top of the overhead that we are already having. There are techniques like zero knowledge proof, but yeah. And it also adds to the complexity of the solution. If it's deployed on the model on servers that is trusted by the model owner, you also safeguard the model intellectual property. So that is good. But in the end, you see that both with homomorphic encryption and on-device machine learning, there are a lot of trade-off to be made. And we would like something that can be easier to adopt and that protects, that satisfy all our constraints. That's where confidential computing comes in, and it can bring value to the problem of machine learning inference. So confidential computing, at least how we are using it, will be doing the computation on the server side. The trust assumption, to be fair, is weaker than the two other technologies because we are hardware-based. We need to trust the hardware. But if we are willing to make this concession, then we get, and if we look back at the 5 metrics we got, in terms of performance, we will see that we can have very low overhead, like between 0% and 10%, nothing compared to what we've seen previously with homomorphic encryption. And you can also, because you deploy on a server, it's you can have powerful server and you don't have to deal with the performance issues of user devices. It has also the potential of being easy to use because basically it's just another applications that you deploy on your server, and people are used to deploy applications on their server. Of course, that being said, there are still some roadblocks that because confidential computing is quite a young technology. So actually, if for instance, you don't use our solution, but you are just someone who wants to deploy his model, it can be quite hard because there are a lot of things to consider when developing a confidential computing solution. But that's where we can come in, people who are working in the confidential computing field, in order to bridge a gap and kind of abstract away the intricacies of the hardware to enable a user. Then, in terms of security, we get, if we design properly our solutions, the privacy of user data, the model execution integrity, and we also get to protect the model intellectual property. And we will see that we protect it even more than just running it on a trusted server, because there is a lot of things we don't have to trust thanks to confidential computing. So Now, let's dig a little deeper into what technology we're using, because there are a lot of technologies and chips that features confidential computing. One of the most battle-tested, because it's one of the early implementation of confidential computing, is Intel SGX. It protects data in use, like other confidential computing solutions, and it ensures the confidentiality of data that is running inside it. Because Intel SGX is a technology that creates some secure areas in memory, and then you can load your code inside it, and it protects the data that is manipulated by your code from being accessed or tampered with by anything outside of the code that has been loaded. So even the operating system and other parts of your software. So that's very powerful, and it is also attestable. That is to say that you can have a proof that this is happening. There are some limitations, of course. You have to trust the hardware, and the Intel SGX threat model, sorry, does not include advanced hardware attacks. So you still have to trust a little bit the infrastructure where it's running, but it's already a big thing compared to what we have today. So that's where we are going to see the issue with transparency and especially security in today computing world. So the issue is with security is usual. Conventional application will have a very important, huge trusted computing base. The trusted computing base is the set of all the hardware, the firmware, the software components that are really critical to the security of your server and the computation. So even if there is the word trust in the trusted computing base acronym in the TCB, it's not something that we like, because actually this means that each time we say we trust something, actually it means that if it's compromised, then everything might be compromised. So we have to verify the integrity and the trustworthiness of every component that we trust. And it's very hard when there are things that from the hardware, the BIOS, the hypervisor, the operating system, even usually things that are not in the control of your control or the control of the person that is running the application. For instance, if it's in the cloud, he might not control, he will not control usually the application. The SaaS provider, for instance, won't control the hypervisor or the BIOS. So what we'd like to do is what we like to have is a smaller TCB, because a smaller TCB reduces the attack surface, and it also means that there are less things to be checked in order to make sure of the security of your system. So the idea, and that's what that's the big pro of using Intel SGX. Intel SGX memory location that is protected is called an enclave, and it reduces the TCB by removing the TPM, the disk, the BIOS, the hypervisor, the operating system, and the other apps from the TCB. You just basically have to trust the enclave and the CPU. You also have to trust a little bit of the RAM, but for all matter of purposes, we can ignore this for now. It's very good because, as I said, it minimizes the attack surface, so it makes your solution more secure. It's also easier to verify because with fewer TCV elements in the TCV, you just ask, for instance, to check that the enclave is secure, and if the user trusts that, if it thinks it's trustworthy, then it can trust your system. So in the end, it boosts confidence in the security of your application, and it's very important in fields that are particularly sensitive, like finance, healthcare, or defense applications. So now that we've had an overview about, now that we've basically introduced confidential computing and what it can bring to the table when it comes to machine learning inference. What I'm going to go a little bit deeper today is a short introduction of exactly what BlindAI, our secure art solution, is, and how we ensure that the security that it satisfies the security that we wanted, because we will see that there are numerous challenges, threats that have to be taken into account, and we will show that BlindAI is a trustworthy solution because we've taken into account all those constraints when we're designing the solution and when we were implementing it. Finally, we'll see that we've asked an independent lab to audit our solution, and we will kind of see the feedback and what they bring to the table. So, BlindAI. So BlindAI comes in two parts. There is a client and a server side. The client that we provide is for the client we provide a Python library. This library will be able to, for the data owner, send the model, and for the end user to execute, to run the model on its input and get the result. And it will handle all the checks that we need in order to make sure the solution is trustworthy. That's where, to dig a little bit deeper into how we make sure it's, to see what we mean by making sure it's trustworthy, we have to get back to the attestable part, the attestation that is provided by Intel SGX. So attestation is what enables a remote entity to establish trust with the enclave. It contains elements about the security of the platforms that the code is running on, for instance, the CPU, and it also contains a measurement, that is to say, a digest, a hash of the enclave, and the attestation is the measurement is here to contain all security relevant information about the enclave. The main component of this measurement is the MR enclave, which is the measurement of the enclave. But there are other things about memory attributes and CPU attributes that we need to take into account. So how does it work for BlindAI? So for BlindAI, what happens is that we are using a workflow in order to make sure that the communication between the client and the enclave are secured and are are protected end-to-end between the client and the enclave. So first, we need to, what we do is that the client will ask for the enclave for information about and for that will like a TLS certificate, an SGX quote, and some collateral information. Those elements will be able to link the TLS certificate with the hardware components and what code has been loaded in, so that we can get guarantees about what the client, what the enclave will do. All those evidence will be checked using the SGX code verification library. And only once it's checked, then a TLS communication channel will be established. And this means that all further communication will be attested. But of course, there is the question of in the slide about how we check that the attestation is valid and how we know how the client knows to which code is trustworthy. For that, when we generate the enclave, when we compile it, we create also a file, which is the enclave manifest, and it's embedded in the client library. It describes what the enclave is, all security relevant details going from the MR enclaves that I talk about, and also information about if we allow debug mode or not, and some attributes about the CPU, basically what we allow to be executed inside, what state the CPU can be. What is key is that on the check attestation validity and TLS certificates part, this check will be done using this document. It will compare what the yet to be identified enclave is that he wants to connect to with this document, and only if it's the right enclave with the right properties, it will connect. Because this manifest is embedded inside the client when the package is created, the user can audit it before using the solution, and he can make the trust decision. He can audit the code, he can say that it's trustworthy, and then it won't have to worry about a silent upgrade like what could happen in a regular server, where the server is upgraded with a malicious package and then it leaks the data. There is no possibility for that. The client will need to be updated in order for the client to communicate with other enclaves than what has been previously agreed upon. So now let's look a little bit about general threats and defense that we can implement. The threats that we're talking about are threats that will impact either the integrity of the execution or the confidentiality of the data that is being manipulated inside the enclave. The list, of course, is not exhaustive. There are other risks, but I want to show what are the main threats, and how taking them into account at the design stage can really make all the difference, and how even with all those vulnerabilities that we've heard around confidential computing and Intel SGX, we can still make secure systems. So the first threat is around regular software vulnerabilities, because Enclave are still running regular software, and software are not immune to bugs or vulnerabilities. So as an example, so usually what we see is that around 70% of all CVEs, so those are the reported vulnerabilities, here's an example at Microsoft, but it is industry-wide. Around 70% of them are due to memory safety bugs. So if we can remove them, we already increase a lot the confidence that we can have in our system. And as a matter of fact, we've seen that there have been a paper by researchers that is named T-Rex that shows that, not surprisingly, not without surprise, they found memory corruption vulnerabilities in a lot of Enclave. It's a paper that is a few years old, but it shows that we would like to avoid this risk. So what we did in order to basically avoid this issue altogether is that BlindAI Enclave is built, is coded in Rust. And Rust is a new programming language that has guaranteed memory and type safety. It's at the same level of abstraction, or it's similar in terms of what it can do to C or C++, but with those guarantees. So we could say that we've already removed like 70% of potential issues. So we should already be happy with that. But in addition to that, because Rust is a more modern language, we also get basically a static analyzer that is built in right into the compiler. We get thread safety, and we can be a lot more safe when it comes to concurrency. Also, we have the Rust is a very minimal runtime, so it's good for auditability in order to and it's easier to adapt to run inside the SGX ecosystem. Another thing to consider is, and I think it's not highlighted enough, is that the Rust ecosystem is very security conscious. And that means that we can, there is a community effort in, for instance, code review to review the dependencies, the most used dependencies, and then publish your assessment of it. Those tools are Cargo Crave and Cargo Vet. As the name suggests, you vet dependencies. So those are very good sign, because it's hard to find the same kind of things in other languages. Also, because even in Rust, you can have unsafe code, but so code that can still not be memory safe. But by wrapping the code, we kind of we will limit the size of the code that we have to worry about. So it really helps people, because code is maybe written once, but then it is edited like 100 times, you know. So, and then in kind of security sensitive application, you read it a lot in order, and you audit it in order to make sure that everything is done properly. So if it's easy to read and easy to make sure that everything is secure, we are a lot more confident that there is not a hidden bug that will kill the security of the software. And finally, I think both those elements means that usually we've got high quality dependencies, and it's very important because you build software on top of other libraries, and you cannot do everything on your own. So you are reliant on them for a lot of the work. So about that, so now I will here's basically an illustration about all the components that are running inside the enclave to provide the services, the remote machine learning services. And of course, there is our neural network inference engine, which is tracked, but there is also a network stack in order to communicate with the outside world so that we have a Python library to help people use our solution, but we could also extend to other things because it's quite easy. You just have to worry a little bit about the attestation, but if you have an HTTP client on your client side, you can use our solution. And finally, of course, we've got some cryptographic libraries, some things to secure the communication. All those components are really important in terms of security. So we really like that they are trustworthy. We really want them to be trustworthy, especially on the cryptographic side, where we know that it can be hard to do. Finally, all of this is, all of our code is based on the Fortanix Rust EDP, which is a framework, a development toolkit in order to build secure enclave and have it compile to target Intel SGX hardware. So, and they are kind of at the frontier of the outside world and the enclave. So we'll see that it's relevant. Let's look at a big threat when it comes to confidential computing. Is that because there is still an attack surface in confidential computing. We've reduced it a lot, but then there remains a boundary between the enclave and the entrusted world. And actually, it's a bit of a peculiar boundary because it's not something that is usual. Usually, you trust your operating system, you trust the underlying components, so you don't expect them to be malicious. That's why it opens like a new, it's kind of game changers, and researchers have had a lot of fun with that. Unfortunately, I mean, it's interesting, but for security purposes, it's a worry that we need to keep in mind. And what the Fortanix EDP is providing is a byte stream abstraction and sanitization between the outside world and the inside world with what they call user calls, which are a very small and you've got very small and properly designed things that sanitize things in between. So that provides a lot of security. If you, I mean, even if usually you've got this attack surface, if you design your things properly to take into account those things, actually you can come up with something that is very secure. But you have to be careful with that. One thing that the Fortanix EDP has been pushing is actually to provide a very simple, minimalist interface, that you don't have complex calls, complex instructions that goes in the ABI, and they've adapted part of the Rust standard library in order to use that. So when it comes to the application code, you have to deal with, for instance, the network, because there isn't basically, you just have a byte abstraction. So when you need to have, if you want a higher level communication protocol with your client, you will need to deal with that. But in Rust, it's quite safe, and network libraries are designed to deal with untrusted inputs. So there is no surprise there, and it kind of boosts our confidence in the solution. Another threat that we've got to consider is software side channels. Software side channels are also a new threat at least they are not completely new, but they are a bigger concern in the world of TEs. Because what happens is that compared to the usual things, there is a gap between the enclave and the CPU. For instance, a compromised operating system that can control the enclave, for instance, schedule the operating system is in charge of scheduling it. It's in charge of the memory paging, as we show on the right. So all those things means that, and of course, it can monitor and log some information that it can observe. So all those things means that actually the operating system gets a lot of power, even though it cannot in any way directly access the enclave memory because the CPU prevents it. It can get a lot of information around how the enclave works, what kind of noise it's making around it. In order to show a little bit, because people can usually not take side channels very seriously, because usually it's very hard to exploit in conventional things, in conventional systems. So here's an example from a paper, which is a control channel attacks, deterministic side channels for untrusted operating system. And as you can see, this is a case where people have been putting like lib JPEG, which is something to read images, to show images. And on the left, on the original part, it's what they've put into the system. And on the right, you can see what was able to be recovered just, of course, just seeing this kind of leaking information. And of course, we can see that it's a huge threat to the confidentiality of the data. You cannot, with this kind of attack alone, compromise the integrity, but you can get information about the user data, and that's something we want to prevent. For that, the best approach, the most battle-tested approach, is to use constant time programming. There are basically 3 rules with that, which is you do not branch on secret data, no condition on secret data. You should not make memory access or write at address that are computing with secret data, and you should not use leaky CPU instruction on secret data. Of course, all those rules are a bit hard, can be hard to use, but to apply. So it's important to take that into account early on. If we go back to our enclave, we look at 2 parts that are very critical. Of course, it concerns the interior enclave, but what is dealing with sensitive data or sensitive secret needs to be hardened a lot more. So the first thing is cryptography, and you have to be careful because the risk is a leakage of your enclave private key, and then people could take the identity of your enclave without there even leaving a trace. So you could have like identity usurpation in this case. So the solution to that is that we are patching the cryptographic library so that it enforces a constant time cryptography. For instance, and we want to avoid fallbacks on potentially unsafe things. For AES we want GCM, we want to basically force AES, NI, and something in order to make sure that the multiplication that is done in GH is done properly. So now looking at the side channel in application code, it's a lot harder because there are a lot more code, but and also the compiler can add to side channel when optimizing. So what we do is we do a best effort approach where we use dynamic instrumentation with valgrind, where we taint the secret and then we see if it is used in a branch. There are some limitations to that. It's not exhaustive. It's quite slow. There are false positives and it can be hard to interpret. And rule number 3 that we mentioned is not covered. Still, it gives it can still identify most venue of leakage, or at least the ones that are really exploitable. And what we would like in the future, also as a future improvement in our solutions, because we're open source, you can even contribute if you will, is to add those tests directly in the CI and not doing them manually. Another threat, last big threat that we'll mention is the end-day attacks. TEs are not perfect. They are not some miracle solutions that will protect you against all threats. But Intel and all manufacturers usually pushes and find a way to patch the potential vulnerabilities that can be found. But then you need to patch quickly. And that has been an issue because usually it's hard to upgrade systems. A research paper shows that, for instance, two major software enclave, the enclave in such secret network, and the enclave that is about power DVD to protect Blu-ray was also vulnerable during, I think, a long period of time, like 6 months, because of that. So you want to plan for that. I mean, you want to avoid these things. It's complex, I have to admit, but if you plan for the worst by, for instance, in our case, using CI/CD in order to be able to release the new versions quickly, if you plan by making it easy to upgrade, for instance, you might want to avoid, or at least you should design it properly, but we avoid, for instance, dealing with distributed system inside an enclave because those are hard to upgrade. Also, you want to avoid long-lasting state or secret. In our cases, if the enclave goes down, there is no permanent state. People just need to re-update, re-upload their model, and then the user can put their input. So there is no long-lasting state or secret. So it makes it very much easy to upgrade. You just swap basically your binary, and then you're ready to go. Of course, there might be some updates that you need to do on the firmware side, but at least on our part, we try to be very agile and able to react quickly to that. Another aspect is transparency. What really the attestation prove is what binary is being executed in the TE. But it only brings transparency if the binary is created by a process that is reproducible and that can be accounted for. So what we really try to do is to make sure that our enclave can be reproduced byte for byte, so that other people than us, so they don't have to trust us blindly. They can check that if they trust the code, they will get the same binary. How we do that is that by building in minimal control environment like Docker, and we also build the enclave twice in order to make sure that there are no spurious things that could cause things not to be reproducible. It's not bulletproof, but in practice we've seen that it's it gives a good level of assurance that things will be reproducible. Also, For transparency, you want to optimize for auditability. So you want to keep things simple, kind of resist to the temptation of adding too much features in your enclave. That's what we did on BlindAI. We want also to be careful in our choice of dependencies. We try to minimize them, not, for instance, putting a too complex HTTP stack in our system. And you want to use well-known and reputable crates, even better if you can check them. So because also there are some specificities of SGX, so you want to look out for them. That's what we are doing. Of course, it's something that you need to do along your process. Okay, so now I'm gonna finish up. We've seen a lot of threats and a lot of defense. As you can see, it can be quite complicated also in that way to audit this kind of solutions. So and to make sure that we've not forgotten anything. So what we did is we asked an independent lab, in our case, to audit our solution. It was a 40 days audit by Quarks Lab. It happened during between January and March. And we're happy to announce that there are no major issues or exploitable vulnerabilities that were identified. You can find a little more information about and the detailed report in the link below. Just to give a preview about that and a few elements that are covered in the report. For instance, here what they said about the attestation, they tried basically to do a man-in-the-middle attack where they modified some inputs, that was happening when the client asked information to the enclave to know if it's trustworthy or not. And they found about the attestation checks that were done, that they did not find any way to bypass those checks. So in the auditor's language, I think we can say that it's secure up to what they were able to investigate. That's very reassuring. Something else, I won't go into details because we are running short of time in time, but they've also, I think for people who are interested in SGX and security, you will be happy to see that they've, in the report, they've done a review of all non-attacks that they could find. And they classify them in some categories. So if you are interested in that, please have a look at the report. Quickly, even with all those vulnerabilities, be assured that we can protect ourselves, because even when there is vulnerabilities, there are many levels where we can fix things. Intel pushes microcode patches. New CPUs are usually designed with the vulnerabilities removed. Of course, we need to check that in the attestation evidence, but you can be reassured we are checking that things are up to date. For the software, if the things cannot be patched directly on the firmware or hardware level, then there can be compile time mitigation, and we just have to check that they are really enforced when compiling. Here's basically the only few vulnerabilities or information that they identified. It's mostly informational issues and something about potential denial of service. I'd like to thank the Quarks Lab auditors. It was very interesting to talk, to kind of see their approach to trying to assess the security of our solution. And I like to thank all the BlindAI contributors that have worked on the project in order to make it more secure. And thanks to you, to the people who've been listening. And I think we've got a question, you told me.
Yes, we do have a question from Chasm. So he's not sure if he understands, but can he only perform inference on models hosted by Mithril Security, or can he perform inference on his own models? And can he install BlindAI on his own server?
Okay. Okay, so 3 points. Actually, the first thing about the models that can be used, we are self-hosting some servers, for demonstration purposes, and so you could use those. But you have also the possibility of pushing of self-hosting your model, and then you can, of course, choose to host any models you like. And for that, we've got, you can find in our documentation how to install BlindAI. Of course, you will need some hardware that is compatible with SGX, but if you've got the right hardware, you will be able to run a code. Does that answer your question?
You could answer in the chat if he wants to, or he could ask another question. We have 2 minutes left, so just give him a second to type another question if he has one. But thank you for your time. That was a great presentation.
Thank you. And thanks to the Confidential Computing Consortium for hosting this talk.
Oh, no problem. And disabled, but he said thanks. Well, thank you for coming. The webinar will be available on YouTube later, so you can always watch it there. So, have a great day, everyone.
Have a great day.
Thanks. Bye-bye.